Hello, my amazing students. This is Mrs. A, and I am in the car driving again. We had a great weekend, and now it's time to go home. But we are doing 4.5 because that's the last section that will be on your test. And the first problem I'm going to do for you is determining domain. And I have two problems here. And remember, when we're talking about the domain of a rational function, we're always looking at the denominator. So here we know that when we factor this denominator, we're going to pull out an x and we're going to get x plus 2. Okay, so in this case, x cannot be 0 and x cannot be negative 2. So our domain is going to go from negative infinity to negative 2 union negative 2 to 0 union, and then lastly 0 to infinity. Okay, so that is the interval notation of that domain. So now the second one we have down here on the board is going to factor as x squared minus 4 is going to become x plus 2, x minus 2. Okay, so what I'm going to do is use the one I just wrote right above it, and I'm going to change it a little bit to be the domain for this function, because it really isn't easy to do this in the car. So we're going to exclude negative 2 and positive 2. So this one right here is correct. And then it's going to go from negative 2 to positive 2. And then lastly, from 2 to positive infinity. So just by changing a few things, I now have the domain for the new function. So those are your first two problems, and the board's a little glary because of the light outside, but there's your board for the first two problems. The next problem is number 19, and we're doing a vertical asymptote. And the vertical asymptotes, again, are going to be determined by the domain. But in this case, when we look at the domain, we end up with being able to pull out an x. And then we factor a 2x and an x. And then we're going to have a minus 3 and a plus 1. And let me look at it here carefully and see if it actually does foil together to give me what I want. And it does. Okay, now on first look I might say, okay, I have a vertical asymptote at 0 and at 3/2 and at negative 1, but I would be wrong, because notice that I have a 0 at 0. And so when I have a 0 and a vertical asymptote at the same place, I end up getting a hole in my function there. So we will say I will have a hole at x is 0, and then I will have a vertical asymptote only at 3/2 and negative 1. And then I still have what would be a 0 at 0, but it's going to end up being a hole instead. So I have no other x-intercepts there because I have the x cubed on the top, but the x on the bottom is going to make that a hole, and so I have no x-intercept. It will only be a hole. So that is problem number 19. Let's see if I can get the glare off of it. Alright, so now we're going to go on to problem number 20, which is also a vertical asymptote. Okay, so the first thing I have to do is factor the denominator. So when I factor the denominator, I get x and x. And if I do an 8 and a 4, so I'm going to do plus 8 and a minus 4. So that has nothing to do with my numerator there. So on this problem, I do have two vertical asymptotes. So I have vertical asymptote at negative 8 and positive 4. And then, it's not asked in this problem, but our 0 is at -5. So we have a 0 at -5. Okay? So that is problem number 20. Okay, so now we're going to work on horizontal asymptotes for a little bit. Horizontal asymptotes are going to occur where this is where our horizontal asymptote cuts the axis, and for all default problems where the denominator on the bottom is greater than the power in the denominator is greater than the power in the numerator, or degree of the numerator, just like our parent function. Remember, our parent function is 1 over x. Okay, and we know the 1 over x function always has a vertical asymptote at 0 and a horizontal asymptote at 0. So it looks like this. Okay, so any function that is a rational function that has a degree in the denominator is greater than the degree in the numerator, it is like the parent function and will have a horizontal asymptote of 0. And this one is a 4th degree in the denominator and only a 2nd degree in the numerator, so this should have a horizontal asymptote of 0. Okay, now the second problem down here is an x to the 5th on the top and an x to the 5th on the bottom. And whenever we have x to the 5th and x to the 5th, then same powers or same degrees in the numerator and the denominator, we're going to get the fraction of the lead term. So this x to the 5th has a 1 in the front, and this x to the 5th has a 1 in the front. So the horizontal asymptote is going to be 1 over 1, or just 1. Okay, now if, just for clarification, if this lead coefficient was a 2 and this lead coefficient down there was a 3, then we would get a horizontal asymptote of 2/3. Okay, so now that I've changed the problem, I'll take this one off of there. Okay, so horizontal asymptote of 1 for the real problem 24, but now we've just mutated problem number 24, and so now its horizontal asymptote is 2/3. Okay. So now we're going to find the horizontal asymptote here. And notice that I have a degree 3 in the numerator and a degree 2 in the denominator. So this one has no horizontal asymptote. No horizontal asymptote. However, it should have a slant asymptote, which is also called oblique. Okay, so it should have a slant or oblique asymptote. And to find that slant or oblique asymptote, we're going to divide the numerator by the denominator and only be concerned with the linear portion of that division. And so here we go on with more. Alright, so now we're doing problem number 31, and our job here is to find the oblique asymptote. Now remember, when the numerator power or degree is higher than the denominator degree, we have no horizontal asymptote, but we should have an oblique asymptote or a slant asymptote when the degree in the numerator is just 1 more than the degree in the denominator, which is what we have here. So what we're going to do to find that oblique asymptote is we're going to do long division, and we're only going to be concerned with the whole number portion here. So we're going to say x squared goes into x cubed 1x times, and I'm going to put the x over here on top of the x portion there, or the x place, and then I'm going to multiply. So x times x squared is x cubed, and then x times 2x is a 2x squared, and then x times a negative 1 is a negative x. And now I'm subtracting, so I will change each sign as I go across. Okay, so I changed all the signs, and now I add. This should always go out. That's my check. And then I get a negative 3x squared plus 2x. Okay, so now I am going to bring down my negative 4, and I'm going to divide again. So x squared goes into negative 3x squared, just the first one into the first one. That's going to go in negative 3 times. The negative 3 goes there. And really, I'm done. What I'm doing now is just the check to make sure it works. Negative 3 times x squared is negative 3x squared. And negative 3 times 2x is negative 6x. And negative 3 times negative 1 is a positive 3. And then I'm changing my signs and adding. And that one goes out. And that's really all I need to go and do, because all of the remainder and what's left over after I get this x minus 3 is not needed. I have my slant asymptote right here. This is a linear function, x minus 3. I've got my slope and my y-intercept. I could graph that line. So y equals x minus 3 is the line that is going to be the slant asymptote. So that is number 31. Let's see if I can hold it so the glare is not on it. Okay, so now we're going to do 37. 37 is kind of all together, like a one big problem where we're going to work on asymptotes, we're going to work on our domain, our x and y intercepts, and graph this thing. Okay, so now, all right, so the first thing we're going to do is look at the denominator and the numerator and see what kind of problem we have. So we've got an x squared is over an x, which means we're going to have a slant asymptote, no horizontal asymptote. So our vertical asymptote is usually the first thing I do. So vertical asymptote is at a negative 1. So that's going to be at x is equal to negative 1. And then our domain has to exclude negative 1. So our domain will be from negative infinity to negative 1, union negative 1 to positive infinity. There's our domain. Okay, so what about our zeros? And our zeros are going to occur where our numerator goes to 0. So when I factor the numerator, I'm going to get an x and an x and a 3 and a 1 and a minus and a minus, and those factors will give me the numerator. So I have a 0 at x is 1 and x is 3. So let's say x is 1, 3 to take care of both of those. Now remember that my zeros are also going to become my x-intercepts when I write them as points. So I'm going to write my x-intercepts. My x-intercepts are 1, 0 and 3, 0. Okay, now y-intercepts happen when I let x be 0. So when I take and I plug 0 into the numerator, I'm going to end up with a 3 in the numerator and a 1 in the denominator. So my y-intercept is 3. Okay, so there's that board. Make sure you get all of that down, because in a minute I'm going to put this board down and you won't be able to see it because I will be graphing all of this information. using it to graph this rational equation. Okay, so now put that down, and here we go, we're going to graph. So from the information that I just showed you here, we have a vertical asymptote at -1. So here's -1, and we're going to make, to the best of my ability, a vertical asymptote. We've got a stoplight here, very fast stop. Okay, so vertical asymptote at -1. A little bit crooked, but you got the idea. Okay, we have zeros at +1 and +3 are our zeros. Okay, and then we've got an x-intercept at those points, and we have a y-intercept at 3. So we'll say 1, 2, 3 is our y-intercept. Okay, now remember what our function is. We have our numerator is in degree greater by 1 than the denominator degree. So we're really not quite ready to graph it. We have to find a slant asymptote, don't we? Okay, so let's come over here. I'm going to get another little board, and we're going to do that division. So we have x squared minus 4x plus 3, that we're going to do long division by x plus 1. Okay, so we're going to go first into first, and x goes into x squared. X times x is x squared. X times 1 is 1x. We are subtracting, so we change both signs, and this goes away, and we have a -5x plus 3. X goes into x, -5 times. Okay, -5 times x, -5 times 1. I'm subtracting, so both signs change, and I wind up with that canceling out. This x minus 5 is my horizontal asymptote. Okay, so everybody can see that. So now I'm going to come back here, and not horizontal, excuse me, that's slant asymptote, not horizontal. Slant is y is x minus 5. Okay, so now I have all of my information, except I have not graphed the slant asymptote. The slant asymptote has a y-intercept of a -5 and a slope of 1. So a y-intercept 1, 2, 3, 4, 5, and a slope of 1. Up 1 over 1, up 1 over 1, up 1 over 1, and I have this slant asymptote. So there we go. Okay, so if it's going to be 1, 2, 3. Okay, I've made it a little bit too steep, so I'm going to make it a little bit flatter, because by the time it gets up to the line, it should be going through 5 and not through 3. Okay, so this has got a slope of 1, and since it started at -5, when it goes up 5, it'll go over 5. So it should hit at 5. So now we've got our slant asymptote, our vertical asymptote, and now we just have to figure out what's going to go on. And remember, my asymptote rules tell me that when I jump over a vertical asymptote, the sign of my graph will change. So the first thing I know is I have 2 zeros in here, and I have this kind of I got a y-intercept there, and I've got this asymptote here. So I'm thinking that this is going to come from here, it's going to come down here, maybe make kind of a sharp turn. I don't know for sure, but maybe not quite that sharp. Who knows? We're going to have to plug in a few points. But then it should come through here, and it should follow that asymptote line. Okay? And then, since it has to come in low on the other side. You see what little bit of room I have here for the bottom of this thing, okay? So basically, there can't be anything here because that is above this horizontal asymptote line. So I'm thinking that when this graph is said and done, I'm going to have something down here in that little bitty part there, but because my graph goes off the grid. Now, when you're doing these, I would do them by hand, but then check them with your graphing calculator. Okay, so I'm going to try to find a graphing calculator and show you what this one looks like. Okay, so remember, this was our function that we're doing, okay, and this is kind of what we came up with. I said, okay, probably comes down and then goes back up, and then down here below, way down there, because that right there was a 5, and then this has got to be down lower than that. So what I had to do when I put it into the graphing, now when you're doing this, always make sure that you see how I entered it into the graphing, if I can hold it still here, is always put parentheses when you are entering it in, and then when I graph it, notice that it looks pretty much, they don't graph the asymptotes, which again, remember, on a test I want you to graph the asymptotes, but they're showing this part that matches. It doesn't look like it goes down below. I made ours go down a little bit below, and really we have to get some more points to figure out just what it does. Probably goes a little bit below, but I had to extend my window quite a bit. So this is a 30-point window going vertically because I went up to +10, but then I had to go down to -20 because I didn't see this lower part that is way down here at the bottom of this graph. I didn't see that until I had extended my graph all the way down to a -20 there. So hopefully you can see those parts. And again, I'm sorry I can't hold it any stiller than that, but it looks pretty much like what we graphed it. But use your graphing calculator to check, especially when you have those slant asymptotes.